So today we're going to be looking at three typical exam questions that you might get on Green's theorem, which is a great theorem. Okay, so let's just have a quick look what it is. When we have a simple curve C completely enclosing a region R with the path going anti-clockwise, Green's theorem connects the line integral and the double integral. Here is the line integral around the closed curve C, and we've already dealt with these line integrals before. And here is the double integral. Now, another way of looking at it for a two-dimensional vector field F, if we look at this, this is actually the curl of F, and if we look at this, we've done in previous videos that is actually another way of doing the vector field F dot dr. Now, just this is a layman's explanation here that I've put here. It's not mathematical, but basically, let's just have a quick look, get a bit of space. So the curl of a vector field is defined as the limit of the average rotation around it. So if let's imagine that we just have a closed curve here, and let's imagine that we just take one of these little tiny points here, and the curl basically is in the limit we go around that line integral there, around this little area here, and basically the sum of all of the sub-region curls within the region cancel each other out, leaving only the line integral around C. Well, basically, so all of these little tiny curls here, I mean, let's just imagine that we have our curve here like this, and we go around our curve like that. Let's just imagine we split it into two. Okay, well then we would go, and that one there, that curve there is C1, and this curve here is C2. Well, we can see if we go around C1 like this, we go up that bit there, and if we go around C2, we go down that bit there, so that bit cancels itself out. Now, if we split it into four, and we would go, let's say here C1, and here would be C2, and here would be C3, and here would be C4. We'd go round C1 like that, and then we'd go round C2 like that, and that would cancel out here. And then we go round C3 like that, and that would cancel out the internal bit because it's going in the opposite direction. And then when we go round C4 there, that cancels out and that cancels out. So all those four internal bits cancel out, leaving us only with the outside line integral, and basically that's what it's saying. That's why it works. Okay, now there are three types of questions, so let's get on with them. So here's the first one. So what we're doing here is we're going to find the value of a double integral by evaluating the line integral, and the question they always ask is basically find the area either of an ellipse or a circle using Green's theorem. Okay, so basically there's a little bit of a sort of a trick here, that if here we let m equal minus y and we let n equal x, then dn dx equals 1 and dm dy is minus 1, which means 1 minus minus 1 is 2, which means that either of these two are equal to half of the area of the thing enclosed by the curve. So basically all we need to do this is we either need to integrate around the curve x dy or y dx to find our area. So let's just draw our ellipse like this. Okay, good, well, that's not too bad. So and then we have b here and we have a here, and we're going to use the parameterization, let x equal a cos of t and y equal a sine of b sine of t, and therefore dy equals b cos t dt. So all we need to do now is we need to do this. So basically the area is equal to the integral around the curve of x dy, which equals the integral, and t will go from 0 to 2 pi, so that's t equals 0 to 2 pi of x, which is a cos t, times by dy, which is b cos t dt. And this is a relatively simple integral to that equals ab, the integral between 0 and 2 pi of cos squared t dt, which is ab over 2 integral between 0 and 2 pi of cos 2t plus 1 dt, and that there comes out to being ab over 2 sine 2t over 2, sine 2t over 2, add t between 2 pi and 0, and that equals AB over 2 times 2 pi, which equals pi AB. So that's another way of getting the area of an ellipse using Green's theorem by taking advantage of this, that the area is equal to that. Okay, so that's question 1. That's a relatively simple one, relatively well. Now, more common in exams is question number 2. Okay, so here's question number 2. So here we're finding the value of a complicated line integral by evaluating the double integral instead, because partial derivative m with respect to x and partial derivative m with respect to y are very simple, and that makes it very so. Here we have a line integral which is an absolute nightmare. I wouldn't even begin to know how to do that line integral, but if we look at this bit here, which is m, and we look at this bit here, which is n, we notice that, let's just get a bit more space here, dm dy is equal to, dm dy is equal to minus 1, because, and dn dx here is equal to 2. And so therefore, we can use Green's theorem to convert this line integral to the double integral dn dx minus dm dy per Green's theorem over dA, which equals the integral over the region R here, and this is the region, we'll come to that in a minute, we haven't even bothered with that yet, of dn dx is 2 minus 1 dA, which equals the integral over, the double integral over the region R of 3 dA. So because dn dx partial derivative and the partial derivative of dm dy, even though these are horrendously difficult functions to integrate, because their partial derivatives with respect to x and y respectively are so simple, that we end up with a very simple integral here indeed, which we don't even have to bother doing in formal way, because basically all we need to do is find the area of this triangle, or the area of that triangle, that's 2 and that's 2, so the area of the triangle is clearly 2, so that equals 3 times the area of the triangle, and the area of the triangle by inspection is 2, which is 3 times 2, which is 6. So therefore we know that the value of this line integral here is equal to 6. So whenever you see a complicated line integral and you think, oh my god, how am I going to ever work that one out, the first thing you should do is differentiate this bit partially with respect to x and differentiate this bit partially with respect to y, and hope that they come out at a very simple thing indeed, which you can then use Green's theorem to solve. So that's number 2. Okay, that's the second type of question. Now the third type of question is this type of question here. So basically they're asking us to do both the line integral and the double integral. So what they're asking us to do is they're asking us to evaluate the line integral, and then around this shape here, and then they are asking us to use Green's theorem to confirm it using double integration. So we have to do both the line integral and double integration. So this is actually going to be a little bit of a long question. Okay, so let's get going. Right, now let's start with the line integral. So what we need to do is we need to go around this shape here. So let's have a look. Let's call this 1 and this 2 and this 3 and that 4. They are the 4 lines, and we basically have to do these 4 line integrals separately. So let's have a look. Here's 1. So this is, I'm now integrating over this line integral here, going from here down to there, and then I'll do that one there, and then I'll do that one there, and then finally I'll do that one there, and I'll add them up, and that will be the sum, that will be the total value of the line integral there. Okay, so for the first one we have x equals minus 1 always, because it's a vertical line. Okay, that's quite easy. And y equals t. From, now we have to be careful here, we are going this way, so t goes from 4 to minus 1. So t from 4 to minus 1, not the other way round. So dx here is 0 and dy is dt. So all we need to do is we need to stick all this lot into here, into the line integral, and that will give us 1/4 of our answer. This is going to be quite long, this is, and that's going to basically be minus, because Because dx is 0, this whole bit we can ignore for this particular line integral. So that's going to be equal to minus the integral from t equals 4 to t equals minus 1 of 6t minus 9 times minus 1. I'm just putting y equals t there and x equals minus 1 there, dt, which equals the integral from t equals minus to t equals 4 of 6t plus 9 dt. Okay, so that equals minus 6t squared over 2, add 9t between minus 1 and 4, which is, let's flip it around and get rid of that minus sign there. I should have done that at the beginning. So that's 3t squared, add 9t between 4 and minus 1, just makes it a little bit easier. And that equals 48, add 36 minus 3 minus 9, which is 84 plus 6, which is 90. Okay, so that is the value of our first line integral, is 90. Now let's have a look at the second line integral, which is this one. I know that's getting a bit messy, but y here is always minus 1, so now it is x which will be the value of t. So now let's have a look at the second line integral. We have y equals minus 1, x equals t, and we go from t equals minus 1 to t equals 1. So here, so that's t from minus 1 to 1. Okay, and therefore we have dy equals 0 here and dx equals dt here. So the line integral now is t equals 1, t equals minus 1, minus t cubed dt. So this time dy is 0, so we can ignore this bit this time, and we're only looking at this bit. And so therefore, sorry, where am I? Whoops. Sorry, my apologies. Yep, that's right, sorry. And so all we need to do now is just evaluate that, which equals minus t squared over 2 minus t to the 4 over 4 between 1 and minus 1, which equals minus a half minus a quarter minus a half minus a quarter, and that all cancels, so that equals 0. So that line integral is 0. That's number 2. Number 3 line integral is this one. Well, this time again, we have that x has the positive value of 1 all of the time. So basically we're looking at y going from minus 1 to 2. Okay, so let's have a look at the third integral here. So the third integral, x will be 1 all the time and y will be t for t equals minus 1 to t equals 2. Okay, so we have that dx equals 0 and dy equals dt. So now let's do the line integral again. That will be minus the integral between minus 1 and 2 of 6t minus 9 dt, which equals 9t minus 3t squared between minus 1 and 2, which equals 18 minus 12 minus 9 minus 3, which equals 18. Okay, so that's the third line integral done. And now all we've got to do is this fourth one. Okay, well the fourth one is a tiny bit more complicated, but this line here, basically we can parameterize because it's the line y equals 3 minus t. So the easiest way to parameterize that is to let x equal t and y equal 3 minus t, but that actually makes the maths tiny bit difficult. So let's use the parameterization. Sorry, that is the correct parameterization. So we let x equal t and y equal 3 minus t. That is that line. So dx equals dt and dy equals minus dt, and t will go from 1 to minus 1. And that's basically going along this line here from there to there, which is the fourth bit of our line integral. Okay, so that's what we need to do. So our line integral now will be the integral from 1 to minus 1 of 3 minus t. All I'm doing is I'm sticking these into our line integral, minus t cubed dt, add 6 3 minus t minus 9t dt, equals the integral between -1 and -1 of 3t minus, you just got to be careful with the minus signs here, minus t cubed, add 18 minus 15t dt, which equals, let's just add all this lot up, and let's flip the sign as well, make it a little bit easier, t cubed, add t squared, add 12t minus 18 dt, which equals, we're nearly there, t to the 4 over 4, add t cubed over 3, add 6t squared minus 18t between 1 and -1, and that equals a quarter, add a third, add 6 minus 18, minus a quarter, minus a third, add 6 minus 18, which equals 2/3 minus 36. So when we add all of these up, all four of them, 1, 2, 3, 4, we get the total line integral is equal to 90 plus 0 plus 18 minus 36, add 2/3, which is 218 over 3. So that is the value of the line integral. Phew, okay. Now it's asked us, though, that we need to do it using to confirm Green's theorem by doing it as a double integral. Okay, so let's, here's the question again. I knew it would take a whole page, so here's the question again. We've already evaluated a line integral, now we're going to confirm it using double integration. Now, fortunately, double integration is slightly easier. Okay, so here is m and here is n. Okay, so basically we know that that is going to be equal to the integral of dn dx minus dm dy dA, and we know that dn dx here, just differentiating that with respect to x, is 9, and we know that differentiating that with respect to y is x. Okay, so we now have our double integral here, 9 minus x dA, which equals the double integral of 9 minus x dy dx. Okay, now what we just have to work out what our limits are. So y is going to go from here up to here, and x is going to go across from -1 to +1. So we can put the x in here already. That's the x, and we know the y is going to go from -1. All we need to do now is work out what that is, and we already know that that is the straight line y equals 3 minus x. So it's going to go from -1 to 3 minus x. Okay, so now let's integrate this bit here with respect to y. So that equals the integral x equals -1 to 1 of 9y minus xy between 3 minus x and -1 dx. Okay, that's doing the y part of it, which equals the integral between 1 and -1, that's x equals 1 and -1 of, and we have to put the limits in now, so we just got to be a bit careful here, 9, 3 minus x minus x, 3 minus x minus -9 plus x. We do have to be really careful with these negatives. I haven't made a mistake here. And that equals the integral between 1 and -1, just tidying all this up, 27 minus 9x minus 3x, add x squared, add 9 minus x dx, which equals the integral between 1 and -1, we're almost there, 36 minus 13x, add x squared, and finally we can see the finish line because it's a very simple integral indeed. That is 36x minus 13x squared over 2, add x cubed over 3 between 1 and -1, and this had better come to 218 over 3 or I'm going to smash my iPad. Here we go, 36 minus 13 over 2, add a third, minus 36 minus 13 over 2 minus a third, which equals 36, add 36, add 2/3, which, hey presto, is 72 and 2/3, which is indeed 218 over 3. Phew! Well, I'm pleased about that, because otherwise we'd have had a problem. Okay, so there's the third type of question now confirmed. So just to go back, because this was a slightly long one, what we've done in this past bit is we've done the double integral here, which in this particular case was easier. The line integral itself was just a bit fiddly because there were 4 lines to do. And then the question, we also did the line integral, which was basically just going around this line here, which was a little bit fiddly. You just had to be careful with your limits and the directions. The second type of question that we did here, seems a long time ago now, is when basically we have a very complex line integral, but dn dx and dm dy are very simple, so it becomes a simple thing. And then basically the first one is a little bit of a sort of a trick question where they ask you to find the area of something using Green's theorem. Okay, well, I hope you found this useful. If you have, please like by pressing the little thumbs up button at the bottom. It takes about 1 second of your time. And subscribe to the Gresti Academy YouTube channel. Thank you very much.